Welcome to the module Introduction to Contacts, Springs, and Dampers. In this module, you will learn about creating contacts and friction. In addition to this, you will learn about the check interference command, which will be used to find component interferences in the model. To better understand the effect of friction in solid bodies contact, you will analyze a catapult both with and without friction. In this module, you will learn how to disable a motor at a specific point on the timeline. You will also be able to apply contact to the components, specify solid bodies contact friction, and add a spring with damper to the assembly. This module is divided into several topics. Click the topic titles in the list for a brief overview of each topic. In this module, you will examine the motion of a catapult as it is loaded and throws a projectile. The crank will rotate the catapult arm through a belt and pulley to a position where a projectile can be loaded. The crank will rotate 2.75 turns to load the catapult. The motion of the rack will cause the trigger to release the projectile. The mechanism will release the arm and the counterweight will cause the arm to throw the projectile. You will determine the torque required to rotate the crank and load the catapult. You will also determine the displacement, velocity, and force of the loading spring. The solution to the defined problem is divided into the following steps. Create a motion study. Apply friction. Apply contact. Add a spring. Add gravity. Calculate the study. Plot the results. Let's see how to create a motion study and turn off the motor at a specific point on the timeline for the catapult assembly. Click Show Me to launch a demonstration video. The catapult assembly file has been opened. Let's examine the assembly. The crank rotation rotates the arm through the belt and pulley and triggers the release of the projectile through a gear train. The gear train consists of 3 gear mates and a rack and pinion mate. When the rack moves, it will come in contact with the release mechanism and lift the projectile holder door. Rotating the crank shows how the mates work. Notice that both the triggers are moving through each other. We need to provide contact between these triggers. Let's return the crank to the initial position using the undo command. Verify that the document units are set to millimeters, grams, seconds. Right-click the Motion Study 1 tab. Click Create New Motion Study. Make sure that Motion Analysis is selected as the type of study in the Motion Manager. To revolve the crank, we need to apply a motor to the end of the shaft. We want to rotate the crank 2.75 turns in 3 seconds. Click Motor. Ensure motor type is set to rotary motor. Select the edge of the crankshaft for both the motor direction and motor location fields. For motion function, click Distance. Enter 990 degrees, 2.75 turns times 360 degrees for the displacement. And enter 3 seconds for the duration. Click OK. After the motor turns for 3 seconds, we want it to hold the catapult in the loading position while the projectile moves into the projectile tray. We then want the motor to disengage to allow the counterweight to drive the catapult. The entire simulation will run for 5 seconds, so to make it easier to select on the timeline, click Zoom in on the lower right corner of the Motion Manager until a little more than 5 seconds fills the timeline. Click Rotary Motor 1 in the Motion Manager. Right-click in the timeline at 3.4 seconds and click Off. This creates a key that suppresses the motor at 3.4 seconds so that it will have no effect after this time. Now we will set the frames per second to 50. Click Motion Study Properties. Change the frames per second value to 50. Click OK. Click Calculate. Notice that, as specified, the motor rotates the crank by 2.75 turns in 3 seconds. From 3 to 3.4 seconds, the motor keeps the crank as well as the arm stationary and ready to launch. Finally, it disengages at 3.4 seconds when the mechanism begins to move in a not specifically defined motion. A few key elements must still be added to the motion model, however. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about creating a motion study and turning off the motor at a specific point on the timeline for the catapult assembly. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed the simulation. Click Next to continue. We can detect interference in SolidWorks as well as in SolidWorks Motion. The interference detection tool in SolidWorks will detect interference between components. However, it will only detect interference for a single static position of the components. Whereas in SolidWorks Motion, interference can be detected for the motion path of each component. Contacts can be defined between multiple bodies or curves to prevent penetration. In this module, you will learn how to define the contact between solid bodies. Contact is used to define the way bodies react with each other. Within the contact definition, you can control the friction and the elastic properties between the bodies. Contacts between the bodies can be defined in multiple separate definitions or in one definition with all bodies included in a single definition only. The latter one will consider contact between all selected bodies, thus automatically generating multiple contact pairs. While this procedure is easy to define, considering contact for all pairs can be computationally demanding. Contact definition with contact groups ignores contact between parts within the group. Rather, it considers contact between all combinations of pairs of bodies across the groups. It is possible to define a maximum of 2 contact groups. When defining contact, there are 3 friction options which can be used depending on the model. They are static, kinematic, and none. Once you decide which friction types to include in your contact, you must provide the static and/or kinematic velocity and friction constants. Click the arrowhead along the edge to learn more about the static and kinematic coefficient of friction. The static coefficient is the constant used to calculate the force necessary to overcome friction when a body is at rest. The kinematic coefficient is the constant used to calculate friction forces once the body is no longer at rest. In reality, the static friction transition velocity is 0, but numerical solvers, such as SolidWorks Motion, require that a non-zero value be specified to avoid singularity at the origin. Let's see how to detect interference. Click Show Me to launch a demonstration video. A view key is a camera orientation tied to the timeline. Whenever a simulation is created, a view key is created at the beginning of the timeline. This can be helpful in some circumstances, but in our case, we would like to view the start of the animation from several orientations. Therefore, we will disable the playback of the view keys. In the Motion Manager, right-click Orientation and Camera Views and click Disable Playback of View Keys. Click Play to play the simulation in slow motion again, and notice that the 2 yellow triggers move through each other. To stop this, we must add contact between them. Before defining contact, we will introduce a feature which can be used to detect the interference automatically. In the Motion Manager, right-click the catapult assembly and click Check Interference. Click the first projectile holder trigger, and then click the second trigger. Click Find Now. The 2 triggers interfere starting at frame 132 at time 2.620 seconds and remain that way until the last frame. Select the first interference and click Details. We can now see the location and amount of interference. Close the dialog. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about detecting interference. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Let's see how to add contact between multiple bodies. Click Show Me to launch a demonstration video. We will start by adding contact between the yellow triggers. Click Contact. For contact type, select solid bodies. We will keep all contact parameters except friction. Eliminating friction will make the simulation run faster, but may be less accurate. Click the first projectile holder trigger part. Then, click the second projectile holder trigger part. Make sure Material is checked in the Property Manager. Click the Material 1 drop-down and select Steel, Dry. Now, click the Material 2 drop-down and select Steel, Dry again. We will run the simulation without considering the friction between these two parts. Clear friction. Click OK. Click Calculate. When the simulation runs, the trigger on the rack mechanism will now contact the trigger on the projectile holder door and lower it. The following additional contact pairs have to be defined. Projectile to projectile holder door. Projectile holder to projectile. Projectile holder pusher to projectile. Using the procedure outlined in the previous steps, 3 separate definitions would have to be created. In order to save time, we will define contact between these components using contact groups. Click Contact. Under Contact Type, ensure that Solid Bodies is selected. Scroll down to Selections and check Use Contact Groups. Select the projectile in Group 1 and into Group 2, select Projectile Holder, Projectile Holder Pusher, and Projectile Holder Door. Note that Property Manager indicates 3 contact pairs will be considered for the calculation. In this case, the door, the pusher, and the holder will all contact the projectile but will not contact each other. As previously mentioned, if contact groups were not used, 3 separate contacts would need to be defined. For materials 1 and 2, select Steel, Dry, and Clear Friction. Click OK. Now, let's create a contact set between projectile and catapult arm. Click Contact. Click the projectile and the catapult arm. Under Material, select Steel, Dry. Make sure that friction is checked. Uncheck Material. Note that unchecking Material opens up the friction dialog fields for editing. The contact characteristics in elastic properties, determined by the selection in the Material dialog, remain unchanged. Elastic properties will be discussed in the next module. We will define friction values for this contact set because we want the projectile to slow down as it moves onto the arm. Change the value of dynamic friction coefficient to 0.15 and static friction coefficient to 0.15. Click OK. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about adding contact between multiple bodies. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. Here's another question to check your understanding of what has been covered so far. A translational spring represents the displacement-dependent force acting between two parts over a distance and along a particular direction. You specify the location of the spring on two parts. Both linear and torsional springs can be added between components. You can define a force-displacement relation in SolidWorks Motion. Force-displacement relationships supported in SolidWorks Motion are x squared, x cubed, x to the fourth, 1 divided by x, 1 divided by x squared, 1 divided by x cubed, 1 divided by x to the fourth. SolidWorks Motion calculates the spring force based on the relative displacement between the two parts, the stiffness of the spring, and the fabrication or free length. The magnitude of the spring force is based on the stiffness and initial force. The spring force can be determined using the equation displayed on screen, where x equals distance between the two locations that define the spring. K equals spring stiffness coefficient, always greater than 0. F0 equals reference force of the spring, preload. N equals exponent. For example, if spring force equals kx squared, then N equals 2. Valid values for the exponent N are -4, -3, -2, -1, 1, 2, 3, 4. X naught equals reference length. If the spring force is positive, then it will repel the two parts, and if the spring force is negative, then it will attract the two parts. A translational damper is considered a resistive element used to smoothen out oscillations encountered due to outside forces. Basically, it provides resistance against velocity. Typically, dampers are used in conjunction with springs to dampen out any oscillations or vibrations created by the spring. In the real world, bodies and even springs have built-in structural damping, and the damper element can be used to represent this. The damper can be added between components in a mechanism. Additionally, both linear and torsional springs can have damping properties that act as the combination of spring and damper together. Like springs, both the exponent of the damper force expression, linear to plus or minus 4, and damping constant can be specified. Let's see how to add a spring with damper to move the projectile onto the catapult arm. Click Show Me to launch a demonstration video. To move the projectile into position on the catapult arm, we must add a spring. The spring will have a preload to hold the projectile against the back of the projectile holder door. When the door drops, the projectile is pushed into position. Click Spring. Keep linear spring as the spring type. Click the first face and the second face. Set the spring constant value to 0.15 newtons per millimeter and the free length to 13 millimeters. The free length combined with the spring stiffness determine the initial force of the spring. Click Damper and enter a damping constant of 0.01 newtons per millimeter per second. Under Display, set the coil diameter to 4.00 millimeters. Leave the coil turn at 5. Set the wire diameter to 0.5 millimeters. The display settings do not affect the performance of the spring. Click OK. Click Calculate. When the simulation solves, the projectile flies off into space and the arm does not release and the counterweight does not stay level. This is because we are still missing a key element: gravity. Click Gravity. Specify the negative Y direction. Click OK. Click Calculate. This time, the arm is cranked down to the loading position and is held there by the motor while the trigger releases the door and the projectile is pushed onto the arm by the spring. At 3.4 seconds, the motor turns off and the gravity on the counterweight swings the arm and launches the projectile. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about adding a spring with damper. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. Let's see how to create plots for the different parameters versus time. Click Show Me to launch a demonstration video. We will start by plotting the torque required to move the arm into position. Click Results and Plots. Define the plot using forces, motor torque, and magnitude. Select Rotary Motor 1 as the rotational element. Click OK. Notice that there are some oscillations between 3 seconds and 3.4 seconds. These peaks are approximate. They will be discussed in the post-processing module. Now, we will plot the displacement of the spring. Click Results and Plots. Define the plot using displacement, velocity, acceleration, linear displacement, and magnitude. Select Linear Spring 1 as the simulation element and click OK. The spring expands from 6 to 13 millimeters. In the setup of the problem, we specified the length of the uncompressed spring as 13 millimeters. Let's plot the velocity of the spring. Click Results and Plots. Define the plot using displacement, velocity, acceleration, linear velocity, and magnitude. Select Linear Spring 1 as the simulation element and click OK. From the plot, we can see that the spring reaches a top speed of 96 millimeters per second. Finally, let's plot the force of the spring. Click Results and Plots. Define the plot using forces, reaction force, and magnitude. Select Linear Spring 1 as the simulation element and click OK. We will receive a warning about redundant constraints. Redundant constraints may have significant impact on the mate forces, such as forces in the mechanical connections, mates, force defined by the mates, and will be discussed later in the course. The resulting force obtained for this mechanism is, however, correct. Click No. From the plot, we can see that the maximum spring force is 1 Newton. We can see that the spring only pushes the projectile for about 0.1 seconds. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about plotting results. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. So far in this module, you have added solid bodies contact between different parts of the assemblies and done the analysis without friction. Now, you will add a friction between projectile and the projectile holder. To add a friction between the solid bodies, you need to activate the checkbox for friction. To add a static friction, you need to activate the static friction checkbox. Now, we will demonstrate how to analyze the same study with friction. Click Demonstration to launch a demonstration video. In this demonstration, we will study the effect of contact friction on the motion of the projectile. We will use the study we have just created to add friction between the projectile and the projectile holder. Right-click Motion Study 2. Copy the existing motion study. Right-click the motion study and rename it to Larger Friction. Right-click Solid Body Contact 5 and edit the group contact set containing the projectile and projectile holder. Activate friction with the default values for steel, dry. Click the Static Friction checkbox. Click OK. Now, click Motion Study Properties. Set the frames per second to 100. Click Advanced Options and change the integrator type to WSTIFF. Click OK. Click OK again. Click Calculate. Notice that the projectile would not slide onto the arm due to the added friction. Click Save and close the file. That brings us to the end of this demonstration. Click Next to continue. Here's a question to check your understanding of what has been covered so far. You've reached the end of the module, Introduction to Contacts, Springs, and Dampers. Here are the key takeaways from the module. Click each tab to learn more. Here is a chance for you to practice what you have learned. Offline exercises are available for this module. To attempt these exercises, you must have access to a SolidWorks installation. To complete each exercise, download the self-extracting executable file from the eCourse Details page on mysolidworks.com. This file contains the sample models and exercise PDF file for every module in the eCourse.